What's going on, guys? Today I want to talk about unitary operators. I'm going to cover a lot in this video, but again, I don't want the video to go on too long here, just to have this be a little bit self-contained. But again, so we want to talk about unitary operators. So unitary transformations are operators. I'll say transformations. Unitary transformations, and I'm going to break this into a couple of sections here. I want to take a look at the unitary transformation or the unitary operator in terms of the time independent part of the Hamiltonian, and in terms of, you might guess it, or you might have guessed it already, time dependent part. Of H. Now let's recall what H is. So in our Schrodinger equation that we developed, we said that I times the time derivative, I times the time derivative of psi, which is the state, is equal to our Hamiltonian times, actually a little bit more than our Hamiltonian, and typically we want to write it like this actually, I over h bar times the Hamiltonian times psi, and when the Hamiltonian acts on psi, that is the same thing as getting an energy and stretching the state by some factor, and when we stretch the state by that factor, we have an energy. I went over this in previous lectures already, and so the Hamiltonian here we fleshed out also. So the Hamiltonian here is an operator where we have h bar squared over 2m times d dx, the double derivative with respect to x. This is the time independent part. There's no time here. We have a spatial operator here in terms of x, and this is just a constant. And then we have this plus v of t. Okay, this is the potential part, or the part that is time dependent. Okay, and this whole thing here is an operator. Okay, and it acts on psi, and we get an energy out of psi. Okay, and so when we're talking about the unitary transformations, the first thing we want to talk about is what is a unitary transformation. So a unitary transformation is one where we have our unitary operator. Okay, this is our unitary operator, and it might act on psi, and what it gets us is just psi in return. So it doesn't stretch it, it doesn't rotate it, it doesn't do anything. It's just an operator that has acted on a state to reveal or to produce the same exact state. Okay, so there's no coefficient out here. If there was a coefficient, it's 1. Okay, similarly, if we have our associated bra state and we need to complex conjugate u in order for this to be true, in order for this statement to be true here. So this is the definition of a unitary transformation. The unitary transformation has to be Hermitian. Okay, so I haven't gone over what it means to be Hermitian. So Hermitian a Hermitian operator is one in which we have, say, U looks like this. It's a matrix, okay, it's a complex matrix, and it looks, say, for example, U looks like this. So this is an example. And if we complex conjugate U, so U complex conjugate, we just take all the elements in here, all the complex elements, and we complex conjugate them. So this is the complex conjugate of U. And then if we transpose the complex conjugate of U, we get U back. Okay? In other words, U dagger with this line right here is equal to 1 I negative I, and here all we did was we flipped these two about the diagonal like that. Okay? And this is what it means to be Hermitian. So Hermitian operator condition, so the Hermitian operator condition is basically that U must equal U complex conjugated and then transposed across the diagonal. Okay, so that gets a lot of the basics out of the way. So let's do this now. So I'm going to go to another slide. So I'm going to start here with the Schrodinger equation in a slightly different notation, like this. Okay, where this dot here represents the time derivative. This all right here is what this equals. And again, here I had it written, the time derivative is equal to this right here. So that's basically this right here, okay? Okay, so now if a unitary operator just doesn't do anything to a state, we can write this. So U operating on psi, this time translated vector is equal to negative I over h bar h times U times psi. Like that. So we didn't do anything. We just multiplied psi by U, and we know that since U is unitary, it doesn't do anything to psi. Okay? Okay, so one thing we want to note now is that U dagger U is equal to 1. Okay? This is basically the statement that when we multiply this matrix by this matrix, we get 1. It's almost like an inner product between two matrices. You can think about it like that. The other thing we want to know, so the other thing we want to know is that U H U dagger is equal to U dagger H U, which is equal to H. Okay? This is to say that if we basically have this unitary operator here, and we act on that unitary operator by this Hamiltonian, not Hermitian. There's a difference between Hamiltonian and Hermitian. If we multiply these two together, okay, and then we multiply it by this, we just get h in return. Similarly, if we did it in this order, we just get h in return after that. So there is really, this is unitary in that sense. And so this is going to help us prove something. So I'm going to take this now, and I'm going to say that since h is equal to this, right here, we have that u prime, not prime, but time derivative, is equal to I h bar times u h u dagger. That's just h right here, and then u and psi. That's just this right here. So we can't think of it like this. Might be easier to put parentheses around everything to keep track of stuff. Okay, so now what I want to do is divert a little bit here. We know from the chain rule that d dt, so the time derivative of this here is equal to the time derivative of u times psi plus the u times the time derivative of psi. This is not the chain rule. Is this the chain rule? I can't remember all the names of the different rules in calculus, but this is basic calculus here. If we rearrange, so I'm going to put a line right here, just to note that we're doing a tiny little bit of a digression. So we can rearrange this equation. I want this here to be on this side of the equation. So u time derivative is equal to, so we just moving this over here. So this minus this, so d dt u dagger minus, actually, minus u dot psi. All right, so now we have this here is equal to this, and this here is equal to this. Okay, so if we could set this equal to this, and so let's do that. So we have d dt of u psi minus u dot psi is equal to I h bar, and that is u h u dagger u psi. Okay, so now we can move this to this side of the equation, and we get that d dt of u psi is equal to negative I over h bar times u dagger u psi plus u dot psi. Okay, so if you're getting lost here a little bit, all I'm really doing is, what I want to do is I want to figure out what the time derivative is. Since the time derivative is an operator, I want to know what it is in terms of the unitary operator, okay? So with this might be a little bit tricky to see here, but I'll try to explain my reasoning. With this, d dt actually, wait, I wrote that wrong. So with this, I had to put an equal sign in there on accident. We have now negative I over h bar times u h u dagger plus I h bar u dot u dagger times u psi. Okay. Now you might think, how in the world did I get to this point from here? Well, this here, if we just take a look here, so this is the same as this. Here, if we were to multiply, this by this, we get the h's will cancel out, okay? The h's will cancel out, and the i's will also cancel out. You can do that. The h's will cancel out, and the i's will cancel out. And then we have this u right here. When we apply this u to this guy here, we just get a 1 out of that. So you can kind of do the foiling out here, and you could see that this indeed does equal this down here. Okay, it might be a little bit hard to see, but it's not terribly hard. Okay, and so what we have now is an eigenvalue problem, where we have that basically d dt is the operator. That's equivalent to multiplying by I h bar times u h u dagger plus I h bar u dot u dagger. Okay? So this is the eigenvalue. Eigenvalue, and this is the operator. Okay. However, we want to know a little bit more, okay, because the eigenvalue is just a bunch of operators. We just managed to figure out what d dt is for any state in terms of unitary operators, and it has a Hermitian operator and a Hermitian Hamiltonian operator in here as well. And so the thing we want to take a look at now is we want to recall that in my first slide there, I said that the Hamiltonian operator has a time independent part we'll call h naught plus vt. Okay, this is the time independent component, and this is the time dependent component. So time dependent component. I got some notes here, so just so I don't make any mistakes, which is why I'm looking down. All right, so if we recall from here, I'll just plug into H this right here, okay? So we have d dt is equivalent to I h bar negative times u times h, which was h naught plus vt times u dagger plus I h bar u dot u dagger. Okay? So we want to take a look now at what this object is. Because if we multiply this out, so d dt is equivalent to I h bar u h naught u dagger plus u v of t u dagger plus I h bar u dot u dagger. So we've multiplied this out. Basically, we've applied the unitary operators to h naught and v of t. What we have left is this, and we want to take a look at what this object is, okay? Such that we just want dt, if we just want dt to have just time components to it. In other words, this is the only thing with a time component to it. As we can sort of visually see in front of us right now, this thing might have a time component to it, but we really want ddt to be to correspond to the time component of the Hamiltonian and nothing else. Okay, because it's ddt. It's so in order to do this, we're interested in I h bar u dot u dagger, okay? And we're going to say, what if u was equal to e to the I h naught t over h bar. So we're going to plug this into this and see what happens. So I h bar u dot u dagger is equal to I h bar, so that stays the same. The time derivative of this here, well, I is a constant, h naught is a constant, and h bar is a constant, so that's just going to leave us with I h naught over h bar times u dagger. So if this is u dagger is just the complex conjugate of this. So that's e to the plus I h bar t over h. Okay, and if we do this a little bit more, we can find out that I accidentally I need to actually write something else in here, because if we remember, the derivative of the exponential here is the argument in the exponential times the exponential again. So I h naught t over h bar, and then we need to put that complex conjugate in there. So that's a plus I h naught t over h bar. like that. So this complex conjugate times its, so this times its complex conjugate is just going to be 1, and that gives us, so the I times I is a negative number, that's -1, and then the h bars cancel out here, and we get negative h naught, and that checks, right? So this here is h naught, this here is h naught, right? Because if we remember from right here, any Hamiltonian applied to, sandwiched in between these two unitary operations is just a Hamiltonian itself again. So this here becomes, so d dt is equivalent to negative I h bar times u v of t times u dagger. All right, if u is equal to e to the I h naught t over h. So I will, actually, I'm not going to circle that quite yet, but I will circle this. So we have, in bold, so we have this guy here. So we found out what u was in terms of, we found out that if we want this condition to be true, if we want the time derivative to just have time components to it, then u here has to be this, okay? And so u here is in terms of the time independent part of h, okay? So the next thing I want to go over is, what is u in terms of the time dependent part of h? And so in order to do that, let's take a look at the Schrodinger equation again. So typically, when we're looking at the Schrodinger equation, we have I h bar d dt, and we're operating on some, oops, the computer blacked out there for a second. So we have u, and I'm going to write something like this now. Actually, I won't. I'll just write the time. I'll just write the, so some state, and it gives us some Hamiltonian again times the state. Okay, this is the time dependent Schrodinger equation. But what we want to do is we want to see how u evolves in time. So we're just going to replace a state. We want to see how u, the operator itself, evolves in time, not this state. So we'll just replace this with u, okay? And u will give you some time components, and most of the time this is how u is written, right? So u starts at time 0, okay? And as time progresses, u also progresses, okay? And this is basically time final right here, okay? And we want to say that this is equal to just the time dependent portion of the Hamiltonian. That's what we're interested in. And times u, because again I'm just replacing here like that. Okay, so I've just replaced the state with an evolving operator, so the operator itself can evolve, okay, in time. So you can think of it as like a matrix that's its numbers are constantly evolving, such that whenever at each time point you can apply at time equals 0.1 or something like that, you can apply the unitary operator to a state and get the state back, okay? But then at time 2 the state might have changed, and so you need a time evolved operator in order to operate on that state again to get the change state back to its not back to its original state, but to the changed state again. Okay, so the operator itself is evolving to compensate for perhaps an evolving state. Okay, and so with a little bit of basic calculus here, we can integrate. So I h bar, and we integrate this d dt. We integrate this thing here with respect to time. And likewise, we're going to have to integrate this thing with respect to time as well. U with respect to time. Okay, and as dummy indices, we have to make time a little bit different here, and because we're integrating over time. So we have to integrate over this value here. Okay, this is a final value, because u will go from here, and then it'll go to here, and then it'll go to here in time. Okay, and so we have to integrate over all that to see to perform this integral. Or we can't integrate to perform the integral, but we have to integrate with respect to something, and we're integrating with respect to time. Okay, and we're going from time 0 to t. Okay, so this integral here just compensates for the fact that this is the thing we're integrating over, the prime thing, but we're just going to t, to this value here. Okay, so what we can do now is basically just a couple more manipulations here. So what I want to do here now is d dt u of t d t like this is equal to, I divide both sides by h. Okay, and then if I divide both sides by h, I can also divide both sides by I, but if I have an I in the denominator, that just makes this negative if I want to put it in the numerator, and you could check that for yourself as well. Okay, that's one of the beauties about I, right? And then we have this right here, and then we have this function here. We have u of t prime and t naught, and we're integrating over t prime like that. Okay, and then this, I believe, also has to be primed. Okay, and so now this here, the integral of a derivative, or the derivative of an integral, is just u. So this here is u of t naught. Okay, and we have to do this now. So we have to say 1 minus I, and then this whole thing over again. Like this. Okay. So now we have, and the reason we had to do that is because at time equals t naught, so when t equals t naught, this thing here is going to be unitary, but this thing here when t equals t naught, at the initial time component, vt might be 0, okay? So then this whole thing just goes to 0, but u of t at t naught has to be 1. Right, so that means that this right here, we have to put this 1 right here in order for that to work out. Okay, so this here is the unitary operator. So I will bold this. So this here is the unitary operator in terms of the time component. You can see how more complicated looking this seems, but I want to offer up a non sort of complicated picture or way to view this. So this is the time. So this is the time dependent unitary operator. Time dependent unitary operator. What I want to offer up a view on which we can sort of read this equation. So what this is telling us is we're performing an integral over this here, okay, where we have some time-evolved object, and it's being multiplied by the time-dependent part of the Hamiltonian. And we're doing this in little integrals of t. So at t0, to t1, so here's t1, okay, what we get here, we can perform this integral right here. So from t0 to t1, we can perform this integral. So v u dt, okay, and then from here to here, perhaps t2, we perform the integral again, and then from here to here, we perform the integral again. So we can perform this integral, and then we just have to multiply it by I over h bar and subtract it from 1, and what we get is eventually, say we want to stop at t4. So say this is t4. We integrate over this little piece here. What we get in the end is u of t 4 to t naught. Okay. So this t here is this t here. So this is the unitary operator as it evolves in time. Okay. And this v here is a coefficient that tells us how much, right here, this v here tells us how much this contributes to the overall, how much this, and then the next v of t will tell us how much this contributes to the overall. Because again, as I talked about in the previous lecture, whenever we have something that looks like this is a wave, right? This is some sort of complex wave depending on what h naught is. Okay. We have so this here is some complex wave, and it has components to it, right? And those components have weights on them. Okay, and those weights tell us how much of each component contributes to the overall complex wave. So we can think of u of t as a wave. Okay? It's a complex wave, and it consists of components to it. So this here was the time independent. time-independent u, and this here is time-dependent u, and then we can begin to make sense of what u actually is in space. And I might add also, this also adds a sense of topology to quantum mechanics. I don't think I'm actually going to go into that. Maybe I will a little bit. So say we have some spatial manifold or some time manifold. It looks like this, right? And here's where t0 is, okay? And what we're basically saying is, as we evolve in time, this time manifold must be smooth all over the place. If it's not smooth all over the place, if it's discontinuous somewhere, then u of t, then we get into some problems on u of t. And there's when we define those problems, we can define the properties of that manifold, and that gets us into quantum topology as well. Okay. But now I want to go over two other things here. So u of t we said was a complex wave. So u of t starting at t0 is a complex wave. We said it looked like this. E to the I h0 t over h bar, like this. Okay. Right here you might be a little bit confused. I just said u here. Again, u is just the same as ut of t0. This t here just tells us at what point in time we want to measure u. Okay, so this is valid. And so this is where Sakurai's book comes in. Again, Sakurai's book does not really go into it in this much depth and this much detail to the point where you can actually understand it. You kind of have to look around other sources and stuff to be able to actually read these equations and understand what they're saying. But if we take a look now, we have, so e to anything, we can approximate it by saying that this is the same thing as, so the constant here is I h bar over t, so I h bar, or h0 over t, or over, not t, over h bar t, minus, since we have this I, it's going to be a minus, but I can actually make it a plus, make this a little bit more, looking like a Taylor series. Okay, and then plus so on and so on. H, this here is really, really small, right? Because Planck's constant is really small, so we can approximate u of t like this, 1 minus I h0 t over h bar. And we call h0 a generator. So h0 is a generator. And the reason it's called a generator, again, is we have this manifold in time, and we're going from t0 to t1, for example. Okay, at t0 we have u of t, t0, and at t1 we have u of t1, t0. Okay, and the means by which we go from here to here, we have to have this h in here, because this is what u equals. So h bar, or h0, helps us go from here to here. So it generates the next unitary transformation. So the energy that a particle has generates what the next unitary transformation is going to be, such that when the unitary transformation is applied to the state that the particle is in, you just get that state back. Okay, so this is h0 is a generator for u of t naught, like that. So h naught is a generator, and v of t is like a weight, okay? So h naught we can think of as a generator, and v of t is like a weight. This is going to help us a lot in understanding equations, because so we know this is a wave, and so the argument in the wave here, the coefficient argument in the wave, is a generator of the transformation, right? And so if we were to go back to some of our earlier lectures on, like, when we said when we said stuff like dx was it had a it was equivalent to multiplying by ik, okay, and we have this thing here, e to the I kx, and if I remember correctly, when we're reading this kind of stuff, k is an eigenvalue, but it's also a generator here, if this is associated with some transformation. Okay. The only one we're actually really particularly interested in is this one, because the energy is a generator for some unitary transformation. Okay, so I'll erase this out. It was kind of a digression. And so we can really begin to understand how to read quantum mechanical equations, and that again is the aim here, is to help you be able to read quantum mechanical equations. And so I want to go into just one more thing here. I want to think about this in terms of matrices. So I'm actually going to move to another slide here, and I'm going to write down this. So u of t, okay, we said that that was equal to 1 minus I h bar from t naught to t. The weight here is like that. Okay, so this is what we derived before. So we can think of this in terms of matrices. Oh, sorry about that. I think my computer is telling me to stop, but I'll stop in a bit. So we have n u of t naught I, and actually I will make this an f. So final state. So u of t, again, it operates on initial state, and it gives us a final state. All right, so 1 here can be represented as a Kronecker delta matrix. So we have ni, and then we have minus I over h bar times the integral of t naught to t, not t naught, but just t. And we have final, the time component, m here. This here is unitary. Again, we've seen that in previous lecture. And then we just write this guy in here, and then we're starting at the initial state dt. Now this is a little bit of chapter 6 stuff, okay, but I think it's necessary to put it into this lecture because this is a way to view this in terms of matrices, because again, this is a matrix. Okay, this is a matrix, and actually I forgot to put something in here. This is a matrix. I'll actually rewrite this a little bit. This here is a matrix with the coefficients, with all the weights in it. Okay, and for each weight we have to apply each weight to a wave, right? So we have this should be NM or FM T, and then we have our M here, U of T naught initial state, like that. Since these are all just coefficients, we can bring this out of the integral. So we have, and actually this N here is an F. It should be an F. So that should be an F. So this again is a matrix in which the initial components are being translated into the final components, and we have weights on those. And we can actually bring this guy out here, H bar F, and then we have V of T M T naught T e to the I omega F M of T U of T naught I, like that. And we need a dt integral on that. We're integrating over T. And that guy there, and that guy there, these guys all have to have primes on them because that's the thing we're integrating over. Okay, and so what this gives us now, this is a matrix formulation of this. So we want to know what this is. We want to know what this is, this object here, what the coefficients are, such that the states remain the same. How do the coefficients have to change such that the state and the initial state equals the final state? Okay, and so we read this as 1 minus the weights. So these here are the weights. The weights on the waves, on the waves, on each wave that evolve in this way. Okay, so again, I know I'm pushing an hour here, but again here we have some time manifold, you can think of it like that, and here at time 0 and we go to time 1, what we basically have is some complex wave here that operates on states, or we could think of it here as U of T. Actually, so we have U of T naught, that's a T naught, and here we have U of T 1 T naught. Okay, and we integrate this over all time intervals, and what we have is, so this is a matrix, this is a new matrix. These matrices evolve, right? So these matrices evolve, and for each matrix here, we have components. We have components that evolve such that we get this state here, and we can figure out how those things evolve according to, we break it down. We break down the time dependent part of the Hamiltonian here. These are the components. These are the components of the time dependent part, or the wave components of the time dependent part of the Hamiltonian, multiplied by this evolving wave throughout the manifold or throughout time, or this evolving operator. Okay, and so this is sort of the first advanced quantum stuff, and it's going to get more advanced from here on out. But this is, I think, a good primer into being able to understand how to read these kinds of equations. Because again, if you're getting into this stuff, you're interested in this stuff, you're going to have to be able to read equations pretty quick, or not pretty quick, but pretty well, so that going through the derivation is actually not that hard. Okay, and that's what I intend to do here. From here on out, it's going to be some more difficult stuff, and I hope you stick with me on this, because again, I'm trying my hardest to break this down to have each video sort of self-contained to some extent, and while at the same time explaining everything as I go along. And so I hope you've enjoyed this this lecture here on Unitary Transformations, and I will see you in the next one. Bye.